Okay, lesson 3 here is kind of our most common application, and I'd say most people probably find it the simplest one too. So here we're looking at exponential growth and decay. So looking at example 1, there are many applications of exponential functions in real life. In most cases, the function y equals ab to the x can be written in some form. So with interest, we change it to be 1 plus I, and something very similar is going to happen here. We're going to make a couple changes, but these ones are a little bit more obvious, I think, than the interest ones. And we talked about this at the very beginning of looking at exponential functions. We kind of said your initial value times the rate to the power of x. So we're actually going to skip here until, let me see here. We'll start with example 2. So the number of fish in a lake is decreasing by 5% each year as a result of overfishing. If the number of fish present is an exponential function, state the base of the exponential function. So remember, we have y equals a times b to the x, so we said b was the rate. We always want to use the rate of the population that is staying. So if we are losing 5% a year, that means we are keeping 95% of the population. So our rate would actually be 0.95, not 0.5. We want to use the percentage that is staying to see what our final amount is. So we'll write an equation to represent the number of fish present after t years. Well, the number after t years is our initial population times our rate to the power of t. If there were 2,500 fish present in June 2002, how many would you expect to be present in June 2017? So that is 5 years down the road. So this is n at 5. It says our initial population is 2,500. 0.95 to the time is 5. That's 5 years later. Plugging this into our calculator, we get 1,934 fish. D, how many years to the nearest tenth would it take to the fish population to reduce to half of the number in June 2012? Well, half of the number would be 1,250. And now we're solving for time. So start by dividing both sides by 2,500. Now we need to get to this exponent. So you could change to log form here or take the log of both sides. I'm going to change to log form here. And your calculator will accept a base of 0.95. So you could type that in and you will get 13.5 years. Example 3, the intensity I0 of a light source is reduced to I after passing through d meters of fog. According to the formula, I equals I0 e to the power of negative 0.12 d. Remember, e is this constant similar to pi that is used to represent growth of populations a lot of the time and growth in nature. At what distance to the nearest hundredth of a meter will the intensity be reduced to 1/4 of its original value? So sometimes these ones throw people off because it doesn't give us an original value and somehow we need to get at 1/4 of that. So it's fine to say that my I0, I started with 1. So that means I would be 1/4. You could choose any value for I0 and the relationship will hold. So we choose something easy like 1. You could choose 100 if you'd rather not work in fractions. So you could use 125 as long as you pick a value and then 1/4 of the value here. So when I substitute in here, I say 1/4 is equal to this. So I substitute in 1/4 and 1. Now how am I going to solve for it? Well, again, you could change this to log form. So we can have this as be log base e of 1/4 equals negative 0.12 d. Remember that we have a special way of writing log base e. You can use this, what we call the natural logarithm, or you can type in log base e Divide both sides by negative 0.12, and you get D equals 11.552, and that continues on. So at what distance to the nearest hundredth would be 11.55 meters? Okay, we're going to skip the developing part and go to the formula here on page 252. So the formulas on the previous page are example of the following general formula which can be used for solving problems involving doubling time, tripling time, half time. So what changes here is for doubling time, our rate changes. So here they've used the letter C. For doubling time, the rate is 2. For tripling time, the rate is 3. For half time, the rate is 1/2. They've also made an adjustment here with the exponent. They said it's T over P, so that's the time. Divide by the period of time for the doubling, tripling, halving, etc. So let's do some examples. A patient feeling ill had a sample of bacteria taken from her throat. The sample contained 387 cells. 24 hours later, the sample was recorded and was found to contain 8,012 cells. Find the doubling period of the bacteria to the nearest tenth of an hour. Okay, so our final amount was 8,012. Our initial amount was 387. Our rate, it wants us to find doubling time, so that means 2. The amount of time this took was 24 hours. And we want to know how long it takes to double. So we want to know the period. So substituting in, we have 8,012 equals 387 times 2 to the power of T over P. So the power of T over P is representing the number of times something has doubled. So in 24 hours, how many times did this double? And that'll be able to figure out, to tell us how long it takes to double. So I would start here by dividing both sides by 387. Sorry, we know T is 24. So now we can either take the log of both sides or switch. I'm going to take the log of both sides this time. So this would be the log of 8,012 over 387 equals 24 over P times the log of 2. Dividing both sides by the log of 2. So dividing both sides by the log of 2, I have log 8012 over 387 over log of 2 equals 24 over P. Okay, so you could multiply diagonally and divide. However, when you think of it, when you solve for P, you would have 5.5 hours. Example 5, in April 1986, the nuclear accident at Chernobyl contaminated the atmosphere with quantities of radioactive iodine. If the half-life of the radioactive iodine is 8.1 days, determine the number of days to the nearest day it took for the level of radiation to reduce to 2% of the original level. So again, this is one of the kind of trickier ones where it doesn't really give us an initial amount and a final amount. So I think it's easiest to say our initial amount was 100, so we're left with 2. You could use 1 and 0.02, doesn't really matter. Our C here, we're looking at half-life, so our rate is 1/2. The time is now what we're looking for, but we were given that the half-life is 8.1 days. So we can use that there. So we have our final amount equals our initial amount times 1/2 to the T over 8.1. So divide both sides by 100. So now I have 0.02 is 1/2 T over 8.1. So again, you can choose to take the log of both sides or change form. I'll change form in this case. Log of 1/2 of 0.02 equals equals t over 8.1. So if you multiply both sides by 8.1, you will get your answer. T equals 45.715, and it keeps going. So we will round this to 46 days. Okay, and we'll stop there.